Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the temperature coefficient. Our objective today is to learn how temperature affects the resistance of a resistor. Specifically, we'll discuss the parts per million per degree Celsius temperature coefficient rating found on 6-band precision resistors, and learn how to use this rating to determine resistance at specific temperatures. Additionally, we'll introduce positive temperature correlation and negative temperature correlation devices, and two variable resistors known as the thermistor and the photoconductive cell. During the resistor color code lecture available at the Big Bad Tech channel, I briefly mentioned a secret fourth property, namely temperature, that influences resistance in addition to length, resistivity, and cross-sectional area. I can't blame you for being mad at me for withholding this vital information until now, but realize I'm withholding a lot of information for you for two important reasons. One, it wasn't important then. It is important now. And two, I operate under the Kung Fu principle, and that I am always entitled to withhold one trick from you, lest you come back at a later date and challenge me. Realize the content I'm delivering via these online lectures are approximations and simplifications only. We could dive very, very deep down any rabbit hole of our choosing and find more accurate and realistic renditions of physical reality, truly horrifying in their complexity. I don't want to though, and neither do you. We have a long way to go and a short time to get there. While temperature effects on resistance might seem trivial in magnitude, I'm including in our discussion of resistors for several reasons. One, we're talking about resistors, and we may as well discuss things that influence resistance while it's fresh in our memory. Two, it's a great opportunity for us to review the 5 and 6 band resistor color code. And three, this is early exposure to the reality of component specifications and performance. We live in the real world, and dogs really do vomit on your homework. Your lab partner really doesn't know what they're doing, and the components you use have real environmental limits, outside of which they can break down and self-destruct. Inside those limits, however, we should be able to predict behavior using simple models that govern performance. One of the most common methods of determining the effect of temperature on resistors is the parts per million per degree Celsius resistor rating. If you haven't checked out the resistor color code lecture yet, I recommend doing so because during this lecture we're going to use the 6-band color code in which the parts per million per degree Celsius rating is employed. As a brief review, recall that the 4-band color code consists of 4 colored bands where the colors signify numbers, and the first band is the first number, the second band is the second number, the third band is the number of zeros, and the fourth band is the tolerance. The 5-band color code inserts a third digit in between the second digit and the number of zeros. The number of zeros and tolerance band just shift over one place to the right to accommodate this new third band, which is now the third number in our resistor value. The 5-band color code is read as follows. First band is the first number, second band is the second number, third band is the third number, the fourth band is now the number of zeros, and the fifth band is the tolerance. Since the 5-band color code deals with precision resistors, it uses some additional colors for tolerance instead of our regular gold plus or minus 5%, silver plus or minus 10%, and invisible plus or minus 20% bands employed by the 4-band resistor color code. They're brown at plus or minus 1%, red at plus or minus 2%, green at plus or minus 0.5%, blue at plus or minus 0.25%, purple at plus or minus 0.1%, and gray at plus or minus 0.05%. Tracking so far? The 6-band color code is just the 5-band color code with an additional temperature coefficient indicator at the end. In effect, if we review the 6-band color code, you get the 5-band color code as a bonus. Isn't that nice? The 6-band, the temperature coefficient, is an indicator of how much this resistor's resistance value predictably drifts as the temperature departs from an agreed upon reference temperature. The color codes for this band represent the following: brown at 100 ppm, red at 50 ppm, orange at 15 ppm, yellow at 25 ppm, blue at 10 ppm, and purple at 5 ppm. The units ppm stands for parts per million, and are actually more appropriately written as parts per million per degree Celsius, or ppm over degrees Celsius. Regarding the term parts per million, something I always for some reason link to the incredible olfactory ability of the shark, it really means exactly what it implies. Just divide something into a million parts. In this case, it's our nominal or nameplate resistance. If, via the temperature coefficient, resistance was to change a number of parts per million per degree Celsius change, you would just divide this nominal or nameplate resistance into a million parts and multiply it times the ppm per degree Celsius temperature coefficient times the change in temperature in degrees Celsius. Every time the temperature changes by a degree of Celsius, the resistance will change by this much. The triangle, or delta, means change in temperature. The change in temperature is calculated by subtracting the agreed upon reference temperature from the temperature at which you wish to determine resistance. If a resistor's nameplate resistance value is specified at 20 degrees Celsius, and the temperature is 20 degrees Celsius, the change is 0 degrees Celsius, therefore the temperature will not affect the resistance, because that's the standard at which the nominal value is determined. If, however, the temperature departs from this agreed upon standard of 20 degrees Celsius, the resistance will change. Consider a 120 ohm resistor with a rather poor temperature coefficient of 5,000 parts per million per degree Celsius. If this resistor was used in a 21 degrees Celsius environment, the change in temperature would be 21 minus 20, or positive 1 degrees. We'd have 120 divided by a million times 5,000 per degree Celsius times 1 degree Celsius. Our change in resistance, sometimes written as delta R, would be plus 0.6 ohms, or plus 600 milliohms. A 120 ohm resistor increased by 0.6 ohms would be equivalent to 120.6 ohm resistor. This does not seem like a radical departure from our nominal value of 120 ohms. However, consider this is only the change from 20 to 21 degrees Celsius. What if this same resistor was to be used in hell, i.e. Georgia, and exposed to 100 degrees Fahrenheit, or its Celsius equivalent of roughly 37.8 degrees Celsius? Operating at 37.8 degrees Celsius means the temperature change from our agreed upon reference standard of 20 degrees Celsius is 37.8 minus 20 degrees Celsius, or positive 17.8 degrees Celsius. Therefore, 120 divided by a million times our temperature coefficient of 5,000 parts per million per degree Celsius times a temperature change of 17.8 degrees Celsius would mean our change in resistance would be roughly positive 10.7 ohms. Therefore, our 120 ohm resistor is now 120 plus 10.7, or 130.7 ohms. This is a roughly 8.9% change in the rated value of our resistor, totally independent of manufacturing tolerance, simply because you're using it in a hellish environment. The temperature coefficient formula does not take into account blood losses from ticks, chiggers, and alligator bites, and the nearly 1,000% humidity encountered in hell. Consider, however, another 120 ohm resistor with a yellow sixth band. This yellow band means it has a much better temperature coefficient of 25 parts per million per degree Celsius. It will ideally not wander nearly as much from our ideal value of 120 ohms as our first example. Let's see if this is the case. 120 divided by a million times 25 parts per million per degree Celsius times our change of 17.8 degrees Celsius only yields a change of 0.0535 ohms, or positive 53.5 milliohms. In this case, our 120 ohm resistor is now 120 plus 0.0535, or 120.0535 ohms. Because of this resistor's clearly superior temperature coefficient, it is for all intents and purposes still a 120 ohm resistor. Granted, it's getting bitten by ticks, chiggers, and alligators and struggling to breathe in the swamp-like air. It's still remarkably close to 120 ohms. In this case, the same change in temperature yielded 200 times less of a change in the resistance value simply because of a temperature coefficient of 25 parts per million per degree Celsius is 200 times less than our earlier temperature coefficient of 5,000 parts per million per degree Celsius. This makes sense. It's a higher quality resistor and more stable over the same temperature range. Consider these two resistors employing the 6-band color code with the following patterns. What are these resistors' nominal values? Given the manufacturer tolerance rating, what is the lowest and highest resistance one might expect to see at the nominal operating temperature of 20 degrees Celsius? And finally, what is the resistance value of these resistors at, let's say, 28 degrees Celsius when we're assuming the resistor is the nameplate value without deviations due to manufacturing tolerance? Pause the lecture and see if you can knock this out. Yes, you should know the color code by now. It starts with a 0. It's a rainbow bookended by a dark end and a light end. 10 digits, 10 colors. Even if you don't know it by now, that hint should have been a dead giveaway. Regarding all the different tolerances and temperature coefficient colors, Even I don't remember those besides the gold and silver bands. I just use this thing called the internet, perhaps you've heard of it, and I look them up if I need to. Our first resistor starts with an orange band. Orange is 3. The second band is red, or red is 2. Third band is green, which is 5. And the fourth band is brown, which means I need to follow this by 1 0. So this resistor's nominal value is 3,250 ohms. Its tolerance band is green, which means it's plus or minus 0.5%. The lowest expected value would be 0.995 times 3250, or 3,233.8. The highest value would be achieved by multiplying 1.005 times 3250, or 3,266.3 ohms. The spread between these values isn't really that big because of this resistor's extremely good tolerance rating. Now, regarding resistance at 28 degrees Celsius, if we assume it was its nominal value of 3250, we'd divide this into 1,000,000 parts and multiply it times its temperature coefficient, where red is 50 parts per million per degree Celsius, and our change in temperature is 28 minus 20 degrees Celsius, or 8 degrees Celsius, yielding us a change of plus 1.3 ohms. In this case, a 3250 ohm resistor plus 1.3 ohms is 3,251.3 ohms at 28 degrees Celsius. Our second example, first band, is brown, which means it starts with a 1. The second band is green, which is a 5. Our third band is a black, which is a 0. And then a red, which means it's followed by 2 zeros. In this case, this is a 15,000 ohm resistor, or 15 kilo ohms. Given it as a brown tolerance ring, of plus or minus 1%, the lowest we'd expect to see is 0.99 times 15K, or 14,850 ohms. And the highest we'd expect to see is 1.01 times 15K, or 15,150 ohms. To determine the resistance value at 28 degrees Celsius, take the nameplate value, divide it into 1,000,000 parts, and multiply it times the parts per million per degree Celsius rating. In this case, a brown band signifies 100 parts per million per degree Celsius, and our change in temperature from 20 degrees Celsius to 28 degrees Celsius is plus 8 degrees Celsius, would yield us a plus 12 ohm change. In this case, a 15 kilo ohm resistor plus 12 ohms is 15,012 ohms. Since we've got two resistors, and it'd be a travesty for me not to drill you on this, let's do a quick review of series and parallel combinations. What does a series combination of these two resistors look like? And what is this combination's total resistance? And what does a parallel combination of these two resistors look like? And what is this combination's total resistance? Let's assume these combinations are operating at 28 degrees Celsius. Pause the lecture and see if you can come up with the same values that I do. The series combination of these two devices are in line with one another, and there is only one path. The series combination of resistances adds up. 3251.3 plus 15,012 could be simplified as a single 18,263.3 ohm resistor. We'll take those results, put those over there, and look at our parallel or side-by-side configuration. In the case of a parallel combination, the total resistance is always less than the smallest resistor. In this case, we would expect it to be less than 3,251.3 ohms. Using the two resistor parallel formula yields us a simplified resistance of 2,672.5 ohms. Hopefully you did pretty good on those simple series and parallel formulas. Let's crank it up a notch now. What if I took our series combination of the 3,251.3 ohm and 15,012 ohm and placed that in series with a parallel set of a 3,251.3 ohm and 15,012 ohm resistor, i.e. I have now created a series parallel relationship. In effect, what I've done is I've placed an imaginary 18,263.3 ohm resistor in series with a 2,672.5 ohm resistor. Since these two imaginary resistors are in series, 18,263.3 plus 2,672.5 yields us a total resistance of 20,935.8 ohms, seen by a source hooked up to this series parallel combination. Let's try another configuration of these same pairs. What if I took the series combination of the 3,251.3 and the 15,012 and placed that in parallel with a parallel set of a 3251.3 ohm resistor and a 15,012 ohm resistor. Again, I have now created a series parallel relationship. In effect, what I've done is placed an imaginary 18,263.3 ohm resistor in parallel with a 2,672.5 ohm resistor. Or if you think about it, I've taken an 18,263.3 ohm resistor and placed that in parallel to our original configuration of a 3,251.3 and a 15,012 in parallel. Regardless of your desired level of simplification or whichever formulas you wish to employ, you'll find the total resistance for this series parallel combination to be 2,331.3 ohms. Alright, before we close up shop on this topic, let's discuss why this temperature effect occurs. Temperature at a molecular level is kind of a measurement of the amount of vibration inside a structure. Think about it. If you had to cross a classroom from one end to another blindfolded, compare how easy it would be to cross if nobody was in there. Yes, the desks are in there and you might bounce off one or two of them, but they're predictable and regular structures. Now, imagine the desks are replaced with water buffaloes with tin pans tied to their tails. You are not going to be able to cross this classroom nearly as easily or unmarred as previously. This is meant to simulate an increase in temperature or molecular vibration of a structure. As temperature increases, vibration increases, and so does the likelihood of an electron colliding with another particle. In short, it's harder for current to go through a hotter resistor because it's running into a lot more moving particles, i.e. the resistance has increased because the temperature has increased. This positive correlation between temperature and resistance is not the only way reality works. This is known as a positive temperature correlation, or PTC. There in fact exist substances that exhibit NTC, or negative temperature correlation, where an increase in temperature decreases resistance. Consider a thermistor. A thermistor is a portmanteau of the terms thermal and resistor, as in thermal resistor or thermistor. A thermistor is your first variable resistor. It is sometimes symbolized schematically as a box with like a little hockey stick slash in it, or a circled resistor with an arrow across it and a T, meaning temperature next to it. I like this one because the arrow modifier is used extensively in hydraulic schematics to mean it is a variable device. A thermistor isn't variable in that there's a thumb wheel or a valve handle you can use to change resistance, but rather via temperature, the resistance varies radically up or down. When I say radically, I mean more so than an ordinary resistor, because as we've learned, all resistors change resistance at different temperatures. This radical change can be used to your advantage. Consider a temperature indicator light, in which a PTC thermistor, i.e. one where resistance increases with an increase in temperature, is employed in series with an LED, or light-emitting diode. It's like a diode with light beams shooting away from it. It's similar to a lamp, except conventional current can only travel in one direction, signified by the arrow on the diode. For a PTC thermistor, when the temperature is below a certain temperature, the resistance of the thermistor is low and allows for greater current to flow through the thermistor and the LED in series. As temperature rises, however, the thermistor resistance increases radically, and the higher resistance chokes off current and the LED turns off. Consider the exact same arrangement, however, using an NTC thermistor, i.e. one where resistance dramatically decreases with an increase in temperature. If the temperature is below a certain value, the resistance of the thermistor is high and allows for very little current to flow through the LED, so it remains unlit. As temperature rises, however, the NTC thermistor resistance value radically drops and the LED comes on. This PTC versus NTC relationship hints at major applications regarding the control of electrical loads like lights, motors, or other actuators. Do you want something to automatically turn on if the temperature is too high or too low? Or do you want it to turn off if it's too high or too low? Sensory devices like thermistors play a vital role in the control of electromechanical systems and are often considered the eyes and ears of such devices. Consider a close relative of a thermistor, a photoconductive cell, often called an electric eye, symbolized by a resistor with light beams shooting into it. You could have a photoconductive cell radically increase resistance in response to increased light intensity, or radically decrease resistance in response to increased light intensity. Such a device would be useful in an invisible safety mechanism known as a light curtain, where entry or exit into an area surrounded by the light curtain would initiate a safety shutdown. We'll go into control electronics, including motor control and the electrical control of hydraulic systems, in much later lectures. For now, though, that's all I got. This was a pretty quick lecture on a pretty focused topic, but we did get a chance to review the 5 and 6 band color codes, as well as practice some series, parallel, and series parallel computations. In conclusion, this lecture took a close look at how temperature affects the resistance of a resistor. Specifically, we discussed the parts per million per degree Celsius temperature coefficient rating found on 6-band precision resistors, and learned how to use this rating to determine resistance at specific temperatures. Additionally, we introduced PTC and NTC devices and 2 variable resistors known as the thermistor and the photoconductive cell. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.